And good morning again, now that we are recorded. So today I will lecture for 3 hours, as I said. On Thursday, I will instead make with you an exercise. I will develop an exercise. We will apply R to compute flow duration curves for the Po River at Ponte Ravoscuro on Thursday. Today we are moving forward with, let me share the screen, with what we started last Thursday, which is some concepts of an introduction. I started with an introduction to rainfall runoff modeling. Now let me just move a little bit the camera here. Okay, and then let me soften a little bit the light. Much better, very good. Let me check if the camera is okay. Okay, very good. And if I stand up, it is fine. Okay, perfect. So we started to describe rainfall runoff modeling as an alternative to inductive, as you may remember, inductive assessment of water resources. We said when we have not enough information to carry out an inductive assessment, then modeling is a solution. And I started by saying that the model is a system of equations that is tasked to describe unknowns. So we have to identify the unknowns in our system, and the unknowns are our design variables, first of all, but we may have additional unknowns, which may be state variables that we need to describe the output variables. And I made the example of the storage in the catchment. I defined the catchment, and I said the storage is essential to compute the output or the river flow, which we are interested in. I said that this system of equation is made by laws, which we can call constitutive laws or equations in the system. And I said that physics gives us the basis in the form of conservation laws, for instance, to describe rainfall runoff modeling. I said that we may include also additional theoretical laws which may come into play if the model becomes more complicated. And I said that we can involve thermodynamics, we can involve chemistry if we want to describe water quality. And this gave to me the opportunity to say that it may be appropriate that we limit the complexity of our models, because I said the complexity is related to uncertainty, and we made a discussion about uncertainty. I said also, when I concluded, that these equations are often expressed in parametric form. This is not a requirement, but I said that if there are parameters in the equations, which are in a way some instruments to tune the shape of the equations, these parameters allows us, by tuning the shape of the equations, or let me say by in a way adapting the equations to the specific case study, these parameters give flexibility, because we need flexibility when we want to model nature, because we have to refer to specific situations where there are specific features. We call them case studies usually. And in order to adapt the model to the specificity of each individual location, we need some flexibility. And this flexibility, we said, it's granted by parameters, which don't change, I said, the shape of the law, don't change the theoretical basis of the law, but on the other hand, for instance, in conservation of energy, we still impose conservation of energy, but we introduce some flexibility, for instance, in computing the energy losses due to friction. So we have coefficients, parameters that we can introduce in order to adapt the general form of these equations to the specific case study. So we already talked about the structure of the models and their complexity. There is an additional a couple of additional considerations. First of all, which I would like to make before getting into the details of rainfall runoff modeling. First of all, another essential feature of a model is the scale. The concept of scale is essential. When you talk about modeling, you should always get information on the scale. What does scale means? First of all, we usually refer in mechanics to two essential scales, the spatial scale and the temporal scale. Scale of representation means spatial resolution, time resolution. So depending on what is the spatial resolution of your model, you may describe, for instance, flow in a river in only one river cross-section or in several of them. If you describe the river flow in several cross-sections, it means that your model is distributed. It's the spatial scale is finer or less coarse with respect to describing only one river cross-section. I think this is understandable. I mean, if you describe a feature in several points in scale, several points in space, sorry, you are getting to a scale resolution that is finer with respect to describing one point only. And the same for time. You may refer, this is simpler to understand, to hourly scale, daily scale, weekly, monthly, annual. Okay, and the time resolution, of course, changes. And you can easily understand that the finer the scale, the higher the complexity, because you have more unknowns, and you may need additional equations to describe your model, to make up your model, or you may require the same number of equations with additional computations. Because, of course, if I have to describe an annual time scale and I want to go down to the monthly time scale, I need to make 12 more computations. So keep in mind this concept of scale. And a second consideration is that I am now making this introduction by referring to rainfall runoff modeling, but actually the same reasoning applies to any model of environmental processes. For instance, today there is relevant interest in climate models. The reasoning that I am making for rainfall runoff modeling, it's more or less the same as for climate models. For climate models, you have equations, and they are derived from physics and from thermodynamics. You may have different level of complexity. You may have several different resolutions. So you may predict only one climatic variable for the whole globe, like temperature, and the model is simple. Or you may want to describe temperature in several locations in the world, and the model becomes more complicated. And the same for the temporal scale. You may find an estimate for temperature at annual time scale, or you may be interested in describing the monthly time scale. And the same reasoning is applied to meteorological models, which make predictions of meteorology. What is the difference between a climate model and a meteorological model? Typically, it's precisely spatial and temporal scale. From the point of view of application, meteorology extends in the future for a couple of weeks today. And if we refer to climate models, then we go into the future for a longer time. Very good. Now, keep this in mind, because the issue of modeling is today becoming an interesting topic. I don't say a hot topic, because hot means fashionable. Interesting means something that is relevant. It's an opportunity. And, but I really would like to say that mathematical modeling of environmental processes is becoming really a hot and interesting topic, because it's related to our capability of devise appropriate strategies for managing sustainability in a larger perspective with respect to rainfall runoff modeling. Mathematical models, they are not just an opportunity for rainfall runoff modeling for everything. And what is the reason? The reason is that when we talk about environment, in general, we don't have enough data to make a reliable inductive assessment. And this is not only a problem of hydrology, not only a problem of water, it's also a problem of climate. If you think that we have climate observations starting from 1850, the time span is very, very small. It's not a time span that allows us to make inductive assessment of climatic features, and therefore we need models. And this is why we use models to try to predict the future climate. This is the main reason, because we don't have enough observation that allows us to make an inductive assessment. And there are, of course, all the pros and cons that I discussed for rainfall runoff modeling, like uncertainty, etc. Okay? And the issue of uncertainty is extremely important because as engineers, we have to avoid to give the feeling that models are perfect. So keep this in mind, models are not perfect. Like any assessment is not perfect, even inductive. And we have to be able to really understand what are the solutions that give more uncertainty with respect to the solution that minimize uncertainty. This is why I'm making this introduction. I think, by the way, that if we focus on rainfall runoff modeling, we can give a fairly nice overview of how a mathematical model works. We will see that there are different levels of complexity, and the same can be applied to several other models of environmental processes. Very good. If you have any question, just stop me. I would like to start with a very simple example to convince you that mathematical models sometimes are very, very, I would say, naive, very simple. And this first example refers to what is called the rational formula. The rational formula is actually a nice example because I think that from a technical point of view, it is extremely interesting because it gives to you the opportunity to very quickly, with a very simple model, to estimate, to get an order of magnitude for the river flow, in a river cross-section. The rational formula is more suitable to compute peak flows, not low flows. And I will explain to you why, but basically because it is so simple, the model, that cannot be applied for simulating every type of river flow. It was conceived to provide an estimate only for the peak, okay? And the reason is that at the beginning, we were more interested in the peaks than in the low flows, because water resources management became, as we know, an emergency only recently. The rational formula is very old. It was proposed in the middle of the 19th century by two scientists that worked independently. It's also an interesting story because one is was a UK scientist and the other one was an Irish. So you know that there is competition between people from UK and from Ireland, and they proposed this formulation independently. This happens quite frequently. When you get the maturity of the theory to gain an advance, it happens quite frequently that independent people or independent teams propose the same innovative result at the same, more or less at the same time. Because, as I said, science progresses usually by first gaining the maturity to provide an advance, which is normally a collective achievement. And then, of course, from the maturity, from the basis, then you have the brilliant idea that comes forward, which may come from two independent sources. And the same is true for instance, what is probably one of the most famous recent scientific advances, which is the relativity theory. The relativity theory, as you know, was proposed by Einstein, but the theoretical basis was set by Lorentz. And Einstein had the brilliant idea, in this case it was alone, a brilliant idea, but actually the maturity of science was achieved thanks to the previous contributions by Lawrence. Anyway, let's focus on the rational formula. And the rational formula applies a very simple mass balance equation. And the mass balance equation basically allows us to say that river flow is proportional to rainfall. Is nothing else than mass balance equation. Like I get on the catchment, which we defined on Thursday, some rainfall. The catchment is a collector, okay? And the river flow that comes out from the catchment is proportional to rainfall. And therefore you see the formula on the screen. Q is the river flow. There is no specification of time because it's the peak. It doesn't describe when the peak happens. It just describes peak flow independently of time. And there is no specification of spatial scale because it refers to a given cross-river section. So you see the simplification. Actually, when I describe river flow, I am expected to specify spatial coordinates and time coordinate. 3 coordinates, okay? Because I have to say the location and the time. In this case, you don't see any dependence on location because it's given for granted, selected given cross-river section, and you don't see the coordinate time because it doesn't specify time. It doesn't say it will happen tomorrow. It says this is the peak, which may occur at any time. And it's given by a coefficient C, which is a parameter. It's a constant. It's comprised between, it's included in the range 0, 1. And then there is rainfall intensity. Rainfall intensity means, for instance, millimeters per hour. It means rainfall depth per unit time. Can be millimeters per second, centimeters per hour, whatever. It depends on the data that you have. And then there is the area of the catchment. So if you think at a dimensional analysis, C is adimensional, no dimension, okay? Rainfall, as I said, is length over time, okay? Millimeters per hour, for instance, length over time. It depends on the data that you have. The area is a square length. So the result is, for Q, is cube length divided by time, which means volume divided by time. It is dimensionally correct. So you can understand that if you multiply rainfall intensity times the area of the catchment, then you get the river flow. And what is the function, the role of C? Is to reduce, to account for losses, to account for water losses. Because you understand that not all the rainfall is finally flowing through the cross-river section. You have evaporation, you may have some deep percolation, infiltration in the deep underground, etc. And also, you may have some storage in the catchment, which means that that water will be released later on. When I want to compute the peak flow, usually I only want to take into account the part of rainfall that immediately contributes to this peak flow. The part of rainfall that contributes to the low flows 3 months later cannot get into here, so it is subtracted through the coefficient C. So you see, it is extremely simple and extremely brilliant as an idea. And it is, you can recognize, nothing else than a mass balance equation. And you may say, you may ask some interesting questions relating to this. Very interesting questions, because there are assumptions underlying here, which I will describe now. There is a complete list of assumptions in my, I think, in my website. We will check. But there are some relevant ones which are important. And if you look at this relationship, you may understand that there are some question marks here. For instance, you may say, this is a question that would be really not trivial. There are some trivial ones, which I leave to you some time to think about and try to figure out in your mind. I don't ask you to say, but to figure out in your minds, what could be the questions here? And there are some easy ones, but the one that I'm mentioning now, it's not easy. You may say, flow is something that is related to water moving, okay? It's volume of water that passes in a cross-river section per unit time. So in some way, conservation of energy must be involved, not only conservation of mass. Because I describe something moving, so you may say, you may ask, where is conservation of energy here? It must be there, must be. And where is? The conservation of energy is in the separation between storage and flow. Because I have rainfall falling over the catchment, but rainfall doesn't stay there. If rainfall was in a way fixed, kept by the catchment, as it falls, then kept there, it would be only storage. And there wouldn't be any flow. And there wouldn't be any need to impose conservation of energy. But rainfall moves and goes towards the cross-river section. And not all of them, not all of the rainfall. Part is retained in storage, and part is finally flowing down. So what I said just a couple of minutes ago is that the coefficient C takes into account this. So basically, when I introduce C, I am also compensating for the lack of an energy balance. This is extremely interesting because it allows you to elaborate on the concept. And I assume that this application of energy balance is, in a way, embedded in a constant, which means that I don't allow for any dependency of energy losses from the amount of the river flow. So C is the same value, even if the river flow is low and the river flow is high. It is extremely simplified. Okay, so this is the first consideration. Second consideration, you may say, okay, but what kind of rainfall intensity do I put there? And this is another relevant question, rainfall intensity. What does this mean? I mean, I can have several values for rainfall intensity. If I look at rainfall measurements, I mean, it can range from 0 to extremely high rainfall. Now, I told you one thing, that this is a formula for estimating the peak flow, so you may understand that probably I have to put some high rainfall there, okay, not just 0. I mean, otherwise it's not meaningful. So you expect that it's a high rainfall intensity. It is an extreme rainfall intensity. Now, so you can understand that in a way, probably there are solutions starting from rainfall data to estimate an extreme rainfall intensity. And you may think of some probability, some statistical technique. I don't want to get into a topic that is related to basic hydrology. If you took in your background some basic hydrology courses, you have probably learned how to estimate extreme rainfall intensity, and people use the depth, duration, frequency curves for rainfall. So we are not repeating this. I just want to point out here that we have statistical techniques for estimating extreme rainfall. And extreme rainfall is estimated depending on 3 features: location. And what is the location here? It is inside the catchment. And the catchment is considered as a whole. So you have to put a rainfall that is representative of the whole catchment. You understand, if the catchment is small, this is not a big issue. If the catchment is the Po River, where should I pick up the rainfall? It's a bit of a problem. But we don't get into the details, just think that the location is inside the catchment, representative of the catchment. The second feature that independent variable that conditions extreme rainfall is the return period. The return period is a measure of the extremeness, let me use this term which doesn't exist in English, of a rainfall data. If you want a very high extreme, very high rainfall, you have to increase the return period. What is the return period of an event? Rainfall event, river flow event, what is the return period? This is extremely important, this definition for you. And the return period for an event of an assigned intensity, so if it's rainfall, it's clear, rainfall intensity. If it's river flow, it's an event of a given magnitude, a given value of river flow. So for an event of an assigned intensity, the return period is the average period of time between two events that have the same or higher intensity. I repeat, for an event of an assigned intensity, the return period is the average period of time between two events of the same or higher intensity. Be careful, you can extend to drought. And the drought intensity is a low flow. So the intensity of a drought is measured in terms of low flows, and higher intensity means lower flows. So just be careful that you can use the concept of return period also for droughts, and therefore for water resources management. It is extremely important that you have this definition well in your background. It may be a question at the exam, but it is extremely relevant for an engineer from a technical point of view. You understand that the return period is related with a biunivocal two ways relationship with probability, because if an event is rare, it is characterized by a low probability and longer return period. So rainfall intensity, extreme rainfall depends on the location, the return period. Finally, it depends on the duration of the event. Rainfall with longer duration is less intense. Rainfall is much intense. It is characterized by a higher intensity when it's short duration. Okay, so now the question is, what is the return period that I have to use to estimate the rainfall to plug into the rational formula? And what is the duration of the event? Okay, good. What is the return period? The return period, let's assume that it's the same as for the river flow. If I want to estimate the river flow for a given return period, I put a rainfall with the same return period there. This is one of the basic assumptions of the rational formula. It is very, it is a very rough simplification, because rainfall and river flow don't have the same return period. But still, it is, it is acceptable for estimating the peak river flow, not for the low flows. Okay, so return period is fine. And keep in mind that usually you are required by law, by the legislation in force, to use for the technical design an assigned return period. In several legislations, usually there is written, do you have to estimate a levee, the height of a levee? Okay, fine. You should use, to estimate the height of the levee, a river flow with a return period of 200 years. This is an example that applies to Italy. Levees usually are estimated for a return period of 100 to 200 years. Or you may say, you may be told, do you have to estimate an artificial reservoir to give water to a water supply system? Good. The size of the reservoir should be estimated in order to cope with a 200 period drought. 200 years period, 200 years return period drought. This is legislation, so this is why I refer to the return period. Okay, so now there is a last question. What is the duration? And I needed to introduce another assumption. What is the duration of rainfall? What is the rainfall duration that is causing the worst peak flow? And this is another interesting consideration that allows you to understand how rainfall runoff modeling works. So if you have a catchment, what is the rainfall duration that causes the critical flow? So think of the Po River, for instance. What is the duration of a rainfall? It's 5 minutes? No. It's 1 day? I would say no. If you think of the floods of the Po River or other big rivers, Mississippi, whatever, and what is the duration of a rainfall that puts the river under crisis? It's typically something like 1 week. So it's not a very intensive rainfall, but it's a long one. Okay, think of a very small creek. What is the duration? It's 1 week? No, absolutely. Normally, a small creek, it's not a duration of 1 week rainfall. It's 5 minutes or 1 hour. For small creeks, it's the thunderstorm that it's really concerning. So why? Why for the Po River I need a longer flow to put the river system under crisis, and for creeks it's just enough 5 minutes? What is the reason? The reason is the time that it takes the flood to form up. So a flood in the Po River, it takes 1 week to form up. And in fact, for a big river, we are usually told 1 week in advance, oh, in 7 days we will have a flood. And for small creeks, we are taken by surprise because they are very, very quick. The floods form up very quickly. And why? Because the travel time of a drop of rainfall to get to the river is very small. In a small creek, it's 5 minutes. So you understand that there is a coincidence, a resonance between the travel time of the drop to get to the closure of the catchment and the duration of the rainfall. There is a resonance. I mean, if they are similar, then it's a problem. And in fact, the assumption underlying, another assumption underlying the rational formula is that I should plug there, I get your question, just let me finish, okay. I should plug there the rainfall with the same duration as the concentration time of the catchment, or time of concentration. Now, we don't know what is time of concentration. It's written on my web pages, but we need to introduce the second definition, and then I give the word to you. So what is the time of concentration? You can, in a way, guess what it means after my previous consideration. The time of concentration is the time that it takes, it's the longer time that it takes to water to reach the closure of the catchment. So the time of concentration is defined as the longer time in the catchment that it takes water to reach the closure. Which means that you should think to a drop of water falling, a drop of rain falling in the most distant part of the catchment, and you should think at the time that it takes this drop of rainfall from the most distant with respect to the closure part of the catchment to reach the closure. This is the time of concentration, which is defined, as I said, as the longest time that water takes to get to the closure of the catchment. And this is the rainfall duration that we should plug there. So there is a question in the room, please.
Just a simple question. Resonance means that they don't have the same trend?
Resonance is not a good term because it refers to periodic processes. So we say resonance when the frequency of a signal is the same as the frequency of another signal. And if they are the same, then they get amplified. Like, for instance, people walking, the soldiers walking on a bridge, they break their pace because if they walk all together with the same frequency as the frequency of oscillation of the bridge, then the bridge collapses. This is resonance. And here I said resonance, but it's not correct. I should have said coincidence. The reason why I used resonance is that it's more evocative in the minds of the students, like something that it is very dangerous. So I used resonance, and it's very, very smart that you picked it up, that it's not correct. Okay? Okay, so the problem is originated when there is coincidence then between the time of concentration and the time of rainfall, so we should put there the rainfall with retro period of the desired retro period of the river flow and the duration of the concentration time of the catchment. And then there are other assumptions that I'm not listing here, I'm not discussing here. What I am, because I'm not really interested in getting from you a list of the assumptions. There are many of them, and they are reported in my website, but I just wanted to give to you the basic ones to emphasize that this is an extremely simple solution that, in a way, solves the problem. And it is very useful from a technical point of view because it allows you to very quickly getting an order of magnitude for the river flow. So sometimes it happens that somebody may come to you for a consultancy activity, and they bring you to a river, and then they say, what could be the river flow here? I don't have any information, I don't have any data. What could be the peak flow that I should take into account when designing something like a bridge, a retention basin, or whatever? And the first thing that you should ask is, what is the area of the catchment? And then, if you have an idea of the rainfall intensity for a given retro period, which, you find several maps available. For instance, for Italy, we have a complete coverage of Italy with maps that give the rainfall intensity for a given duration and a given return period. And if you have an idea of this rainfall intensity, I can tell you, for instance, in Bologna, if one asked me what could be the rainfall with 100-year return period with hourly duration, I would say something like 50 millimeters, 50, 60 millimeters. And basically, if you have an idea of the rainfall intensity, you multiply the rainfall intensity times the area of the catchment. You assume C equal to 1, just to stay on the safe side, and then you get very easily an order of magnitude. And the rational formula is very useful. On the other hand, it's clear to you that it's not very precise, and this is, of course, it is a consequence of the extreme simplification, because you have to take into account that complexity means extreme complexity means uncertainty, but also extreme simplification means uncertainty. You have to, this is quite obvious, and you have to take into account this. So it's clear that there is an optimal trade-off between complexity and uncertainty, and which it's not easy to be found, but in this case it's clear that the simplification is extremely rough. Okay, so I mean, this is a first example, and now here you see that the duration of the rainfall event, there is the discussion that I anticipated. I should have advanced with the slide, and there is a definition of the time of concentration, and these are what I already discussed. Now, let's try to move a step forward in terms of complexity. And in order to move a step forward, it's clear that I have to try to remove some of the simplifications of the rational formula, which doesn't describe the dependence on time, doesn't describe the progress of river flow. The rational formula gives to me only one value, which is the peak. But for my applications of water resources management, the peak flow is useless. What I need is a long-term description of river flow. I need the knowledge, the complete knowledge of the hydrograph. What is the hydrograph? The hydrograph is, just 1 second, I go back to the page. The hydrograph is a graph of river flow against time. I thought I had a link here. It's not here, so let me just look for hydrograph. Wikipedia. So you see here, a hydrograph is a graph showing the rate of flow, discharge versus time, past a specific point in a river. So the hydrograph refers to a specific cross-river section, and it gives the picture of stream flow or river flow against the time. And in this case, you see that the time resolution is daily, because it's Julian day. Time resolution can be different, can be variable, but in order to optimize water resources management, I need this type of information, not only the peaks. If you look here, we have a couple of peaks, I would say 4 of them. And if I add the knowledge only of the peaks, I can't do anything in terms of water resources management. I need to describe everything, including the low flows. But not only the low flows, water resources management is knowledge of the full hydrograph. Because in order to cope with the low flows, to make sure that even when the flow is low, I have water for society, I may build a reservoir to be filled up when the flow is high. So I need, as I said, the knowledge of the full hydrograph. And therefore, this is why we analyze the flow duration curve. Because the flow duration curve takes observations continuously in time. The flow duration curve is based on the knowledge of the hydrograph. When I download the Po River Flow series, time series, it's an hydrograph. And therefore, my model needs to generate an hydrograph. And the rational formula can do that, can't do that. So let's then move this step forward. Let's increase the complexity of the model to describe the hydrograph. Very good. A very good example is the linear reservoir. This is a very classical historic model. It was proposed, I think, for sure before 1930. So it's something quite consolidated, and today is considered too simple. But still, I think it gives very good interpretation. It's a very good step forward with respect to the rational formula. And please note that it's important. So there is a mathematical development, as you will see. Let's learn it because it's frequently asked at the exam, and I think it is significant. So this is why I suggest that you learn it. Now, the linear reservoir is based on the application of explicit application of mass balance and energy balance. The latter, the energy balance, applied in a very simplified way. So the assumptions, the equations, let me say, the concepts are the same as the rational formula. It is the translation, it's the application of the concepts, the translation of the concepts in mathematical terms that is more complicated, is more, let's say, detailed, okay? And what is the basic assumption? The basic assumption is that the catchment is like a tank, is like a reservoir. This is why it's called reservoir. In the name you see the word reservoir. And then for this reservoir we can apply a very simple mass balance equation. Let's indicate, if you look at the screen, with W, depending on time, the storage in the catchment, the water storage. And with T we indicate time. Let's indicate with the symbol P, rainfall intensity. Or let's say here, let me be more precise. Here, P is not rainfall intensity, is rainfall intensity times the area of the catchment. So it's intensity of rainfall in volume, not in terms of depth. With the rational formula, it was depth. Okay, here it's rainfall depth multiplied by area of the catchment. And QT is the river flow at the outlet. You see that the river flow depends only on time, not on X and Y, not on the spatial coordinates, because we refer to a specific cross-river section. So the spatial scale is fixed, and it is given by fixing the cross-river section. So, very simply, in differential terms, you may say that the difference between rainfall and river flow, so rainfall minus river flow at each time step, at each time t, the difference rainfall minus river flow is equivalent to the change of storage into the catchment. Okay, so the dWt over dt is equal to Pt minus Qt. This is quite trivial. And of course, the change in storage may be positive, may be negative. No problem. Storage must be greater than 0. But okay, let's assume that it's greater than 0, of course. This equation is expressed in differential form. This happens quite frequently. Conservation equations, they are often expressed in differential form, which is quite understandable because they describe a change of something. Conservation equations describe a change of something. So they say that energy is conserved. What does this mean? It means that energy change is compensated by something else. If I want to impose conservation of mass, then change in storage must be equivalent to the difference of rainfall minus river flow. And it's not a problem. I mean, the problem is that in order to describe then the variables, if I have an equation describing a change of a variable, in order to describe the variable, and I am interested in the variable, I need an integration. I need to compute an integral. So it is a complication from a mathematical point of view. And this is why sometimes we prefer to find approximate relationship that give the variables already in integral form. But we shouldn't be concerned by computing an integral, because an integral is a sum. So we shouldn't really be, what's the problem of an integral? The problem is, if I want to compute it analytically, yeah, it's a bit complicated. But today we don't have to be bothered by analytical computation. Today we have numerical computation, and numerical computation for an integral, it's just a sum or a difference. It's not really concerning. But there is another concern that you should have. When you listen somebody talking about integration, you shouldn't be concerned by the analytical complexity. You should be concerned by initial and boundary conditions. Because of course, if you have an equation describing a change of something, and you want to compute the something, you need a starting point. So if I have an equation describing a difference, and I want to compute the real value of the variable, I need to know the starting point. So the variable is equal to x0 plus the difference. And this x0 is initial and boundary conditions. And in particular, given that here we describe the storage depending on time and the river flow depending on time, it's the initial condition that concerns me. So the value of W at time 0, because this equation describes the difference W at each time step. So I need to know the starting point, which is W at time 0. Is this clear? And it's this information that should concern you, because we should be concerned not by the math. When we talk about mathematical modeling, we shouldn't be concerned by the math. We are engineers, we can deal with the math. The problem is the information that I need, the data. So this is your concern. When you see a model, you shouldn't be concerned by, I say this because I was concerned by mathematical computation. Today, even today, sometimes some people tell me, use that model, and then I think, oh, maybe this is complicated. But this is something that is inappropriate. It's not a rational concern. We should be concerned only by the lack of information, not by the math. I mean, if other people can use it, you can use it. But other people use the model in another catchment, and they may have the information. You use the model in your catchment, you don't have the information. This is the real concern. Okay, so this is a differential equation, and it is a balance equation, but be careful here. What are the unknowns? You have two unknowns. The river flow, it's your unknown. The rainfall, let's suppose that we know it, because if we don't know the rainfall, we'd have to use a different model. I use rainfall runoff modeling, I said this, because I assume at the beginning that I have rainfall data, okay? It's your input data. We have it. But there is W. W is a variable that I needed to introduce. And what is W? It's a state variable. It's a state variable. I have two unknowns. I need to introduce another equation. And the second equation that I have to introduce must be an equation that gives to me either one of the two unknowns or a relationship between them, clearly, from a mathematical point of view. And what is the second equation that I could consider? But I know from physics that if I want to describe a flow, I need a conservation of energy. And therefore, I could put a conservation of energy. Or, if I want to make it simpler, I can put whatever relationship between W and Q, an empirical relationship relating W and Q. And this is what is done here by introducing a linear, and this explains the first word, linear reservoir, a linear relationship between the two unknowns, between the storage and the river flow, which is, I mean, justified. If I have more storage, I have more river flow. And of course, this empirical relationship, it is, all in all, substituting the energy balance. So this is an empirical substitute in integral form for energy balance. There is a question, please.
Sorry, is this method, I mean, this function, useful always in the previous area? For example, I think it's more useful in previous urban area.
You know, this...
because it's neglecting, sorry, the evaporative transformation and the other factors.
Yeah, okay. So the question is this model more appropriate for impervious areas because it is neglecting other phenomena like evaporation, transpiration, etc. Okay. You are anticipating some considerations that I was going to make within a few minutes. First, when you put rainfall here, it's net rainfall. So it's not gross rainfall, it's net one, which means that losses are taken off here from rainfall. Okay, I could have said this at the beginning, but your comment gives me the opportunity to say this now. So net rainfall, first of all. And now you say, is this more appropriate for impervious areas? I would say that this model is more appropriate for catchments where you have a relevant storage. And because it allows you to explicitly take storage into account in a dynamic way. The rational formula, for instance, it is more appropriate for catchment with a very reduced storage. So I would say that I wouldn't say that this is a good model for impervious basins because in impervious basins, I think it is probably going to overestimate the storage. But actually, you should think about what is the physical soundness of this model, of the equations. So the mass balance is fine. I mean, it's perfectly sound. What is not really sound is this approximation, this linear approximation between storage and river flow. So I would say that this linear approximation is working well. It's working better for huge basins with a large storage. In impervious areas, it's not really going to work well. And this is the problem. So you should just take into account what is the physical basis of the equations and the physical soundness. This relationship, what is the reason why it is introduced? It is introduced because it makes the model very simple. And it makes the model, it makes the analytical integration very simple. We will see. The analytical integration is very, very simple. And so what is the reason why it was introduced? This is a model that was introduced at the beginning of the 20th century, like more than 100 years ago. And they didn't have PC, they had the need to make computations by hands. So this is why they introduced this. And today I wouldn't say that it's a reasonable assumption. It's not. But I still it is a very good example because you will see that again the integration is fine. It's quite easy, and let me see. Here it is. The integration is easy, and I wonder whether we can. Just 1 second. I think I need to show with more detail how it is integrated. So if we combine, let me go back to the PowerPoint presentation 1 second. If we combine these two equations, basically we can we can say that W, that the derivative, the total derivative, it is total because we have only dependence on time. So the total derivative of W divided by over the T is equivalent to, we can write it as K times the derivative of Q dt with respect to time. Basically, if you take the derivative with respect to time of this second relationship of Wt equal to K times Qt, you obtain K, which is a constant, is assumed to be a constant, and therefore you can bring it out from the derivative, that multiplies the derivative of Qt. And therefore we can substitute here, and we obtain a differential equation where we have only one unknown. And the differential equation is basically at the left-hand side of the mass balance equation. You just have to change the derivative of Wt with the product by K and the derivative of Qt. And this can be integrated analytically under simplifying assumptions. And let me just go to this page here. You see that, let me bring this equation in here. This is what you obtain if you substitute for Wt the product between K and Qt. So you get this equation, and this can be integrated by multiplying both sides by e to the power of, let me just show. You obtain this. You multiply both sides by e to the power of t divided by k. This is it's a trick to obtain something that can be easily integrated analytically. And then you bring everything at the left-hand side, and you obtain this relationship here. And here you recognize that the first two members are the derivative of Qt that multiplies e to the power of t over k. Let me just move forward. And we obtain this. I think that it would be nice if I tried to write on the blackboard for those who are, and also for you, just 1 second. Let me try to write on the blackboard this mathematical development. Just let me check if the blackboard is taken by the camera. Not yet. Okay, I have to change 1 second. Okay. Okay, I think that now the blackboard is visible. And let me share the screen. Okay, now you can pin the video on the blackboard, and I can write on the blackboard. Okay. So, our relationships are the Wt over dt is equal to pt minus qt. And then the second one is wt is equal to k, perfect, which multiplies qt. Let me check if everything is yes. Okay, so these are the two relationships, 2, 1. Perfect. Now, we can, from here, we can say that the Wt over dt is equal to K dQt over dt. This is what I said, okay? Now I can substitute there, and then I get K derivative of qt divided by t is equal to pt minus qt. And then I can bring everything on the left-hand side, and then I have k wt over dt minus pt plus qt is equal to 0. Now I multiply everything by e to the power of t over k. Good. And now I write it up. I need to delete one row here. Very good. And now I can write k dq over dt multiplied by e to the power of t over k minus pt e t over k plus qt e t over k equals 0. Good. Okay, now if I take these two terms, 1 and 2, let me delete here. These two terms, I can write them. Let's do like this in order to, let's make another step in order to better understand. Let's divide everything by k, okay? So we get dq t over dt e to the power of t over k. And then I take this one plus 1 over k qt e to the power of t over k minus 1 over k pt the power of equals 0. Everything is okay. And now I can take these two. What is this? This is equivalent to the derivative over dt of what? It is the derivative of qt e to the power of t over k. Because it is the derivative of a product, and therefore you have the first derivative, the derivative of a product, basically you take the first factor unchanged times the derivative of the second. And therefore the first factor is qt times the derivative of e to the power of t over k, which is the same e to the power of t over k times the derivative of the exponent, which is 1 over k. And therefore you get this. The second factor is e to the power of t over k unchanged times the derivative of q dt. Okay, and then this is, I can add this, minus 1 over k p t e to the power of t over k is equal to 0. Perfect. Now I can compute the integral, which can be computed here. Okay, so the integral of the first term is what is between square parentheses. So I can write it in this way, qt times e to the power of t over k, but this is to be computed between two extremes of integrations. So I need to start from 0, beginning of the simulation, beginning of the integral. Let's put it at time 0. And then the second extreme, let's put it at time t. And then here I have to put a tau, correct? Because it's the variable of integration. Okay, very good. And then I have to compute the integral of the second term, which I bring at the right-hand side. And let me just write it as an integral, okay? So I take 1 over k out of the integral, and then here I compute the integral between 0 and t of p tau e to the power of tau over k in the tau. This is my integral. Okay, now let me delete here. First, I anticipate that in order to take an explicit representation for this integral on the right-hand side, I will need to make an assumption. I need to know the rainfall. The rainfall is described by a function, and if the function is analytically tractable, rainfall is analytically tractable, then I may be able to compute analytically the integral. If rainfall is expressed by a function that is not easily tractable, it may be not possible to compute analytically this integral. For now, let's forget about this. Let's keep the integral in this form. So let's keep the sign of integration, and let's discuss later. So let's now manipulate this relationship in order to get an explicit representation for the river flow Qt, depending on an integral that is still to be computed. Okay, very good. Now, in order to get this explicit representation, what we can do is to divide everything by, on the left-hand side and the right-hand side, we can divide everything by e to the power of tau over k. And therefore, we obtain, or let me do like this. Okay, let's write in this way. Q tau computed between 0 and tau is equal to 1 over k, and then here again we have the integral, and let's bring the division by e to the power of tau over k inside here, and this is p tau, and here I can write e to the power of Okay, sorry, I wanted to skip one step, but I don't think it becomes clear. Let me write in this way. Let me start again, because it's not clear in this way. Let's compute this left-hand side. So this becomes qt times e to the power of t over k minus q0 e to the power of minus q0. This is what I obtain, okay? Because e to the power of 0 is 1, okay? And then this is, let me rewrite this. 0t p tau e to the power of tau over k in the tau. Okay, very good. Now I can divide everything by the e to the power of t over k in order to get the explicit representation for the river flow. Okay, so it becomes qt is equal to, and then I go to the right hand side and I get q0 e to the power of minus t over k. Is this clear to you? Because I am dividing by e to the power of t over k. So I can multiply q0 by e to the power of minus t over k. Okay? And then here I can now write plus 1 over k integral between 0 and t p tau. And here I can finally write e to the power of tau minus t over k in the tau. E to the power of tau over k becomes e to the power of tau minus t over k, because I divided what is inside the integral sign by e to the power of t over k. So I can write t minus tau. Because it is the product of two exponentials, and then I get the exponential, which is elevated, the exponential of the difference of the exponents. Okay, and now I am almost ready, and I would say that we have computed the integral. What can you now see here? What is this relationship telling to you? That the river flow is given by a term which is exponentially decreasing, which is an initial condition whose effect is, as time progresses, vanishing, which is perfect. I mean, I have a Q0, which is the river flow at the initial condition, at the start of my simulation, whose effect is, as time goes on, is progressively going to 0, which is perfect, is the effect of the initial condition. Now here, instead, I have the integral of rainfall, which is multiplied by this exponential that you see is, as time goes on, is computing the contribution of rainfall at each time step tau to the formation of the river flow at time t. There are some representations of this model where you see a minus sign at the exponent, and then the exponent is written as t minus tau. It doesn't change anything. If you change the orders of t and tau here, if you change the sign of both t and tau and you put a minus in front of the exponent, it doesn't change anything. I just wanted to tell you that also in my website you will see that it is given by exponential of tau, t minus tau, not tau minus t, but there is a minus sign in front of the exponent. Okay? So again, this linear reservoir splits the contribution to river flow in two components. One is the initial condition, which is progressively vanishing, and the second one is the contribution of rainfall at each time step. Now, how to compute in numbers this result? Of course, you have to compute, you have to make a numerical integration if p tau is not analytically tractable. If p tau is analytically tractable, you can compute the integral. And now let me give you an example. Let's suppose that rainfall is analytically tractable. And what is the simplest way to make a function analytically tractable? Let's assume that it's constant, okay? So let me now write here constant rainfall. And then we can compute the integral, of course. Constant rainfall. Constant rainfall, and let's make a second assumption, Q0 equals 0, just in order to simplify the writing, okay? Now, what can we write? We can write that Qt, let me just remove also this. We can write that Qt is equal to, let's forget about the initial condition because Q0 is 0. It's equal to 1 over k p, which is constant, integral between 0 and t of e to the power of, let me put the negative sign, minus t minus tau in divided by k in the tau. This is what comes out, okay? Good. Let's now compute the integral, which can be easily computed. I can write Qt. Sorry, this was 1 over k, not 1 over p. Okay, there was a mistake here. It was 1 over p. It was 1 over k. Qt is equal to p dt, p, sorry, constant, 1 over k. And now let's compute here the integral, which is precisely e to the power of e minus tau divided by k, which multiplies the integral, I think, here, times k. Okay, this is the integral, and this is computed between 0 and t. Okay, and now we can write Qt is equal to, these cancel each other, P, that multiplies 1 to the power of minus, it becomes 1, sorry, 1, because here I have t minus t is 0, e to the power of 0 is 1, minus, and then it's minus e to the power of minus t over k. This is the result. So if I write, and then we make a break. if I wanted to draw a graph of this relationship, what the graph would be? Let me write it here. The graph of qt depending on time. Okay, so for time equals 0, q is 0. So the graph starts from here. And if time goes to infinity, q tends asymptotically to what? To b. And this is my graph. So what is the linear reservoir telling us? It is telling us, under this assumption of constant rainfall, it is telling us that if I have rainfall constant, which means also lasting forever, that the discharge, the river flow, is asymptotically reaching the volume of rainfall per unit time, which is, if you think at it, it is reasonable. This is net rainfall. It means that if you have a rainfall lasting forever, the river flow at the beginning is 0 and then goes up slowly and asymptotically reaches the volume of rainfall, which is fine. And the rate of convergence is dictated by K. What is K? It's a constant. It's the constant of proportionality of the linear relationship between storage and river flow. And keep in mind, it was defined in this way. Wt is equal to K Qt. So, what is the unit of K? What is the unit of K? This is a classical question at the exam. What is the unit of K? Time. Okay? It is the unit of time. And I can tell you that it can be proved that K in a calibrated model is similar to the time of concentration of the catchment. And K dictates the rate of convergence of this exponential relationship. Okay, now, I don't have finished, but we can make a break here. I just want to say, I decided to make it on the blackboard because I realized that just limiting myself to describing what's written on the web pages, it's not well understandable. And I apologize because I wanted to skip a step, but then I realized that because the blackboard is very small, I apologize that I had to delete every step as soon as I wrote it. But I hope that I could give you an idea of how the analytical integration was computed. Any question? And then we make 15 minutes break. Okay, let's make the break then. Okay, we can start again. What you can see on the screen now is from the tutorial documents, where you see that there is indeed the same equation that I derived on the blackboard with the less steps. And you can see that there is the graph showing the output from the linear reservoir with constant rainfall and Q0 equal to 0. There are a couple of comments that I would like to make. First of all, I am aware that today we marked a step in mathematical complexity in our discussion. This is normal. I mean, you don't have to be concerned if you notice that there is indeed an increase. There has been an increase in the complexity of our discussion. Just 1 second. I am, okay, turning the camera so that the video shows my face. So, I mean, it is normal, as I said, and we are indeed getting into something that it's, from a mathematical point of view, becoming more rigorous and quantitative. It may require also from your side some rethinking of what I did, and if you have something not clear, of course, I'm available for questions. We will mark other steps forward in terms of complexity of the models, and marking a step forward in complexity means that also the mathematical part of it becomes a little bit more elaborated. However, I will be always clear in what I ask at the exam, because I think that getting into the mathematical details is important, because it guides you through the understanding. So by computing the integral, by thinking at what an initial condition means, what an integral means, what is the difference between a differential representation and an integral representation, what is the difference between physical basis and empirical approach. I think that reflecting, thinking of these different solutions helps you in gaining a better understanding. Even if this doesn't sound immediately clear to you, I tell you, believe to me, by making the effort of understanding the math, you gain a deeper knowledge of the concepts and why the concepts are useful to you. You gain also deep knowledge of what is uncertainty and what is the trade-off between uncertainty and complexity. So this is why I also want to get into the details of the integration into some mathematical details. On the other hand, I recognize that you don't have to learn by everything of it. So I will be extremely clear, and also in saying that sometimes in the past, I asked at the exam to good students to repeat the analytical computation that I made today in the blackboard. I think it is something that can be asked, because it doesn't require really a big effort of memory. It requires an effort of getting into it, which I think it is a synonym of the goodness of your preparation. I'm not a fan of learning concepts by memory, but I am a fan of learning how to use the concept, how to develop the concepts. And therefore, this is why I think that this is also something that may be asked at the exam, up to now. Another consideration which is more technical. K is a parameter, as I said. You see that it's a constant. So it matches the definition that I gave to the parameter. It is a constant for a given catchment, but it can vary from catchment to catchment. So it gives flexibility to the linear reservoir to get adapted to several case studies. So it perfectly matches K, the definition of parameter. A good question is how to estimate it. I gave to you a suggestion. I said it is similar to the time of concentration of the catchment. Good. On the other hand, this suggestion helps you in getting an idea of the value of K, but keep in mind that whenever it's possible, you have to be very, very rigorous and precise in the definition of parameter values. Parameter values are essential for the performances of your model. So we have to be very, very rigorous in that. And this means that we have to use all the information. I already mentioned to you that being rigorous in water resources management means using all the information that we have. And so how can be K then better defined? How can I move beyond the indication of similarity with the time of concentration of the catchment? I would say that this is a perfect example of what calibration means. K needs to be calibrated at the end of the story. And calibration means that you compare the model simulation with observed data. If you calibrate a model, it's the best way to check model performances. Again, let's suppose that you have observed river flow and observed rainfall data. You optimize K. It's the only one parameter here. In this model, in this linear reservoir, you have only one parameter, which is K. Let's optimize K in order to maximize the model performances, the model verisimility in the reproduction of observed data. This is what calibration means. You can call calibration optimization, parameter fitting, estimation. So when you talk about, these are synonyms, model calibration, model estimation, model fitting, model optimization, these are all synonyms for parameter calibration. And as I said, the best way is to compare with observed data. Keep in mind, this is a specific feature of water resources management. We believe that model performances are to be checked by optimizing simulation of observed data. Other scientific disciplines don't have the same opinion, but for water resources management, this is what we mean with model calibration. This allows us to make a test and also to assess uncertainty. The best way to assess uncertainty is to analyze the errors made by the model in the simulation of true data. This is the best way. There are other solutions. Other scientific disciplines have different solutions. What we want to do in water resources management is this. And keep in mind that also for an engineer, this is it's a strategy that can be easily defended. Engineers have a responsibility. I already mentioned this to you. They are responsible for their design. You put your signature there, and the signature means that you get responsibility. And if you have to defend for some reason what you did, the fact that you compared a model with the true reality is a very good way to defend it. Okay, and just keep in mind that K is, if you look at the definition of K on the blackboard, and those who are at home, I repeat it, K is defined through the definition of WT, which is equal to K times the river flow. You can see from this definition that for increasing K, you are increasing the storage of the catchment. So just also keep in mind at this implication, which means that if you get larger Ks, larger values of K, it means that you are in a catchment which has a larger storage and a longer concentration time. This effort to assign a physical value to model parameters is another way to make sure that everything is working fine. So if you make a calibration of K and it turns out that K is 1 hour, while you know that the time of concentration of the catchment is 1 week, there is something that it's not really good in that. So you have to wonder why. Model fitting, model parameter calibration gives to you an unreasonable value for the parameters. And this is another indication that you have to take into account in order to evaluate the performance of your model, the goodness of what you did. Just keep in mind that models are based in some way on energy balance, mass balance, other scientific laws, and the parameter values have to, in a way, mirror the concept. So just try to verify if your parameter values are sensible and reasonable. Okay, now, I said that this assumption of linearity is not really the best. I mean, in some cases may be appropriate, in other cases not. And I said also why this assumption was introduced. Because it makes the model analytically tractable. It makes also the model, in a way, more robust. And this gives to me the opportunity to introduce another concept, the concept of robustness. What does it mean, robustness? It means that a model may be not very precise, but it is also unlikely that it's plain wrong. A robust model means that the result, you can trust it. Maybe it's not the best result that you may take from a model, but it's not really something that may generate surprise because of its incorrectness. I mean, so the linear assumption is quite robust. I mean, you cannot expect a really bad outcome from it. On the other hand, of course, you can change the relationship, even if you decided to take an empirical relationship between storage and discharge and river flow. Even if we want to keep an empirical relationship to substitute the energy balance, you may decide to make it a little bit more complicated and maybe to adopt a nonlinear relationship. And nothing wrong in introducing an exponent somewhere in that linear relationship, which means that you, in a way, introduce a nonlinear relationship. In fact, the linear reservoir can be easily transformed in a nonlinear reservoir. And this figure is taken from Wikipedia. There is a Wikipedia page on the nonlinear reservoir. And nonlinearity can be introduced in several different ways. You may have several different options. Let's look at this tank here. This tank, it's completely different from the assumption of linear reservoir. The linear reservoir is assumed to be a tank with a bottom discharge, so that you have an outflow from the bottom discharge that starts as soon as rainfall starts. If you remember the graph that it was on the blackboard, which is still on the blackboard for those who are in the room, you see that river flow starts at time 0, at the same time as rainfall starts, which means that the linear reservoir has a bottom discharge with an outflow that is linearly proportional to the storage. But we could use another scheme, and look on the screen here, where the discharge is not in the bottom. In this reservoir here, you have, at the beginning of the rainfall, you don't have any river flow, because you see that there is a bottom capacity in the tank that doesn't produce any outflow. And then when you reach the level of the first discharge, then river flow starts. What does this mean? It means that the relationship between storage and river flow is no more linear. If you bring in a graph the relationship between storage and river flow for the linear reservoir, it is a rectilinear segment that passes from the origin of the axis. Okay, and in this case, if you look at the screen now, in this case you have at the beginning rainfall with no flow. So you have storage with no flow at the beginning. So you have zero flow for increasing storage, which is rectilinear, okay? But when you reach the level of storage that brings at the first discharge, you get an angle in this rectilinear representation of river flow versus storage, because river flow was zero, and then you have river flow starting to increase. So if you make a graph, you have a first segment in the relationship QW, which is 0Q for increasing W, and then a second segment which marks the threshold of the first discharge. So you see in this tank on the screen, you have thresholds. Thresholds means non-linearity. Thresholds mean non-linearity. Threshold means that if you make a graph QW, you have angles there. But here you see that there is a second discharge, a second threshold, and you may have a third one. And these discharges can be regulated by nonlinear relationships between storage and river flow, which means several levels of nonlinearity. This means also increasing number of parameters, because if you think of this tank here on the screen, you have this bottom capacity with no river flow, it's a parameter. You have to define what is the bottom capacity, the bottom storage that doesn't produce any river flow. It's a parameter. So you have increasing number of parameters. Increasing number of parameters means increasing complexity, and you have to calibrate more than one. But it is very easy, if you make a numerical code, transform the linear reservoir into what you see on the screen. It is very easy. The question is whether the performance is improved, of course. It depends. It depends on the case study, it depends on how well your model is formulated. We will discuss later on about parameter calibration more extensively. So for now, let's just note that there are several procedures that can be used for the purpose for calibrating parameters, and we will discuss them later. Now let's introduce another complication, a more complicated model, something that removes the assumption of linearity while maintaining a certain level of simplicity. And therefore, I want to introduce a third example of a rainfall runoff model. We discussed the rational formula, very simple. We discussed the linear reservoir, a little bit more complicated. The third one is more complicated from the theoretical point of view, and actually the application is more or less the same level of complication than the linear reservoir. And we will make also an exercise later on with R to apply this third model. We can make this exercise because application is, as I said, quite easy. But from the point of view of the theory, it is a little bit, it requires a further effort on your side to understand it, okay? And let's try to make this effort. And then we will see what I can ask at the exam. But let's try to make, independently of the exam, the effort to understand what's going on here, because in this way you can understand what is the the trade-off between complexity, uncertainty, and performances of the model. So the model which I would like to discuss is called the I model. Let me just check, and let me use the slides. And let me, just 1 second, change the camera again, because I want to stand up. Okay, perfect. Okay. It's called IMOD, and IMOD is an acronym that comes from hydrologic model, so it is very simple. And actually, in fact, I should have written IMOD with a capital M, because in the literature it is described in this way. I think this model is an excellent idea to improve the performances of the linear reservoir while maintaining the complexity quite limited. I think it is really an excellent idea. And the idea comes from the awareness of the limitation of the linear reservoir. What is the limitation? One of the limitations of the linear reservoir that we didn't discuss. One limitation, significant limitation, is that the model is lumped. We say it's lumped. What does it mean, lumped? It means that it considers the catchment as a unique entity. And there is no way with the linear reservoir to account for spatial variability of runoff generating processes within the catchment. There is no way. You have a unique rainfall that in the linear reservoir, you have a unique rainfall value that goes into this tank, which is, okay, maybe reasonable. And you don't take into account into the linear reservoir of the fact that even if we had a unique rainfall over the catchment, unique means that the spatial distribution of rainfall is neglected, which, okay, can be fine. I may accept it. But even if I accept the idea that over an area I have the same rainfall at each time interval, even if I accept this simplification, still the linear reservoir assumes that over this area, you have the same mechanism of transforming rainfall into runoff. We don't take into account that, for instance, there are impervious areas over a catchment where you have a full transformation of rainfall into runoff. We don't take into account that we have areas into the catchment with a very high permeability, and here you have a different way, a different transformation of rainfall into runoff. Spatial variability means more than rainfall variability over space. It means also that the processes leading to transformation of rainfall to river flow are spatially variable. Think of an house with a garden. Over the roof of the house, you have the totality of rainfall that is transformed into flow. In the garden, you probably have no flow after a rainfall because you have infiltration. These processes should be considered because this is an expression of the heterogeneity of the water cycle. The water cycle is heterogeneous. Heterogeneous means that in space is highly variable, as we know. And there is a lot of variability, not only, as I said, in the distribution of rainfall, but also in the mechanisms. Or think about the difference in slope of the catchment. There are some parts of it that are extremely steep if you go in the mountains, and the lowlands are flat. And here you have a different processes. The travel time is varying. In the mountains, the travel time is shorter. When you get in the lowlands, the travel time increases. So how can we then take into account this spatial variability. There is a classical solution in the literature, which is to adopt what they call distributed models, which means that you consider the catchment as not a unique entity, but an aggregation of several entities, spatial entities, which exchange flows between them. And let me see if I can find a figure. One second. So if I look for Google in distributed hydrological model, and I look at the images, I think this is, let me see what is, I think, let me start from this one. Oops, sorry. Let me start from this one. And, okay, this one I want. You see that the catchment is represented through a grid. You have a grid, you have cells that form a grid, and if you look at each piece, each grid, each cell of the grid, you see that each cell receives precipitation with different values, possibly, of precipitation in different cells. And you see that the cells, they can exchange flow. They are characterized by different vegetation, different slope, and then they can exchange flow laterally. Or so you can see that the arrows are depicting exchanges, or like in this case, soil-water movement model, and there is an exchange of flow between the cells. And therefore, in each cell, you have a description of the flow, of the surface flow, of the river flow. If there is a river in the cell, it's river flow. If it's a cell without a river, it's overland flow, what is called overland flow, that is traveling towards the river. And we can find more refined pictures, like here. One second. This one. Let me increase it. You see the resolution is low, but you see that there is, with the red arrows, they are depicting the path, the flow path from cell to cell. So each cell is producing an overland flow that is traveling downstream by following the slope of the catchment. So there are, by following the direction of the max slope, the generated flow is propagated downstream. And then it is collected into the river. Here you see that also in the underground, there is a similar schematization. So it means that the flow that infiltrates, then it's routed downstream in the underground. This is another example of distributed modeling. And here you see that there is another figure, which I think it's also meaningful. But the resolution is too low. So anyway, this is another figure that was depicting the various flows. And let me see if, but I think you got it. So this is a possible solution. But this type of solution, it's a bit complicated because, you know, for each cell you have to make a computation. You have to apply the mass balance, the energy balance. So the result is that you have a strong increase of unknowns and an increase of the number of equations. So these models can be applied only if you have a very huge information at local scale. For instance, is rainfall described in a distributed way? So are you able to specify what is the rainfall that falls in each grid cell. If not, probably it is not worth making this complicated development if you cannot describe the processes at local level. Can you describe the land cover at the local level in each grid cell? If yes, then maybe worth applying a distributed model. If not, probably it is not worth the effort. And these models, by the way, gained very high popularity about 30 years ago, starting from about 30 years ago, at the same time when we could easily use the computing power of the new generation of personal computer. So basically, when computational, analytical, numerical computation became more accessible, then more complicated models like distributed models became more popular. On the other hand, we understood that the level of complexity is so huge that the required information is really massive, and also uncertainty is, in a way, was inflated, turned out to be inflated. So about 20 years ago, researchers tried to reach a compromise. So the question was, is there a way to move a step forward in representing the spatial variability of selected processes without using computational intensive models, without increasing model complexity too much? And I think that the iMod model was a brilliant idea because it introduced an assumption that indeed allows to represent part of the spatial variability. It is still a lumped model. So still we have a unique value for rainfall entering into the model as input data, but we have a way, a means here to take into account the spatial variability of the runoff generation process. Because what is here the basic, what is the assumption? The iMod model assumes that, let's suppose that you can subdivide the catchment into many locations, and each location is indicated with the letter I. So the assumption is that at each location in the catchment, we have a different value of the soil storage capacity. What is the soil storage capacity? It is the depth of rainfall that the soil can absorb before getting saturated. So it is basically, the term explains what is soil storage capacity, soil water storage capacity. And the assumption is that this storage capacity is different at each location of the catchment. So where the catchment is impervious, the storage capacity is 0. Where the catchment is permeable, then we have a different from 0 value of the storage capacity. And the model assumes that there is a max value of the catchment of the storage capacity. The mean value is 0, because we assume that in any catchment there are at least some locations where there is 0, the soil is impermeable. And then the model assumes that there is a max value of storage capacity over the catchment. And you understand that this max value will be treated as a parameter. This is an intuition that we may gain. And then how to describe the spatial variability of this essential feature for runoff generation. I mean, the storage capacity is an essential feature for runoff generation, because it's clear that when the catchment is fully saturated, everything that rains over there is transformed into river flow. But when the catchment is not fully saturated, at least in some parts of it, then you have that some rainfall is transformed into storage, not into river flow. So how can we describe this spatial variability between zero storage capacity and what we call with the symbol Cmax? The storage capacity is, we indicate it with the symbol Ci, depends on the location I, and we indicate the max with Cmax. How can we describe this? The model doesn't want to say where the storage capacity assumes a certain value. It doesn't want to say that the storage is max there, there, and there. This is not the purpose. The model wants to describe the fraction of the catchment that reached saturation after a given rainfall. So let's suppose that after 10 millimeters of rainfall, what is the fraction of the catchment that is saturated? This is what the model wants to describe. And what is the fraction after 20 millimeters of rainfall? This is what the model wants to describe. So, how can we describe this fraction? Okay, so let's refer to a generic value of storage. Look at the screen, no? At this relationship. But before looking at the relationship, let's look at the variable C star. C star is a given value of storage between 0 and Cmax. Okay? So the question is, for a given value of C star between 0 and the Cmax, what is the fraction of the catchment that is saturated? And let me just emphasize that if I want to describe what is the fraction of the catchment that is saturated by a storage C star, basically I want to describe the fraction of the catchment where the storage is less than C star. Less than C star. If the storage is less than C star, therein the catchment is saturated. Okay, then the model says, let me say that the fraction is described by this relationship here. It's an exponential function. It's 1 minus. The fraction means that it is variable between 0 and 1, okay? So it is 1 minus something that depends on what? C star, of course, C max, through an exponent beta k. This is what the model assumes. Again, what is this? What is delivering this relationship? What is F C star? It is the fraction of the catchment that has a soil storage capacity lower than C star. What is the shape of this relationship? Let's see. I think I have a shape here. Just 1 second. Let me go to the web pages because I think I have a figure that is not reported here. Here it is. Let me see if it is only one figure. No, it's not only one. So let's look at the figures. These are figures that refer to an hypothetical situation where Cmax is 100. Okay. First of all, what is the unit of C star and Cmax? It's a storage that usually is expressed in millimeters, which means storage per unit area. Okay, and therefore here you don't see the unit, but it is it is varying from 0 to Cmax is 100 millimeters. 100 millimeters is a value that is reasonable for a catchment. It can be larger if there is a lot of permeability, but it is reasonable. Now, if beta is equal to 1 and Cmax is equal to 100, this is the relationship that you get, which is linear. If you go back to the expression here, you see that if Cmax is 100 and beta is equal to 1, you get a linear relationship. Is 1 minus 1 minus C divided by Cmax. And therefore, for increasing C star, you have you start from 0. You see when C star is 0, you get here 1 minus 1, which is 0. And when C star is equal to Cmax, you get 1 minus 1 plus 1, which is 1. Precisely the same that you see here. Oops, sorry. Precisely the same that you see here. It is varying from 0 and 1, Fc, and it's linear. Okay, good. You understand that here I have two parameters, Cmax and beta. Beta is becoming another parameter, which is dictating the shape of this relationship. Now, let's look at another possibility, beta equal 2. Beta equal 2, you get this relationship here. And beta equal 2 means that remember, Fc is the fraction of the catchment that is saturated. If beta is equal to 2, you get a more rapid convergence towards saturation with respect to linearity. So the catchment becomes more rapidly saturated. What it means? It means that if you increase the storage, then it goes rapidly to saturation. Keep in mind that saturation means, means something more dangerous from a flood perspective. Okay. Now let's look at the third example, beta 0.5, and here you have the opposite situation. What are the limiting values for beta? 0 and infinity. It can vary between 0 and infinity. Beta equal to 0 means that you get a flat shape. Fraction remains 0 until you reach the value of Cmax, and then at the value of Cmax you have a sudden convergence to saturation. Beta equal to infinity means that even for small values of storage you get immediately to saturation. This is, it is an interesting idea. I think you can get it, because you can describe some spatial variability. And still, but then I am stopping here, still, this equation is analytically tractable. This model was chosen, this relationship was chosen because it is easily, it can be easily integrated. Because you will see that we will need an integration after a while. Because why do we need an integration? Because this is a contribution, this generates a contribution to river flow. The part of the basin that is saturated doesn't infiltrate rainfall and gives a contribution to river flow. So this means that at each time step you have a different value for saturation in the catchment. And at each time step, depending on the value of saturation of F, depending on the value of F, you have a contribution to river flow. And then these contributions are to be summed over time. And therefore, we will need to integrate this. A relationship similar to this one will be integrated. And the fact that it's easily tractable through integration is a plus. So this was what the reasoning that guided this model. So the reasoning that originated this particular relationship, which is reasonable, It is flexible because it counts 2 parameters. So it is flexible for different case studies, and it is tractable. I would like to stop here. On Thursday, we make only exercises. So we will make the first one, computation of the flow duration curve for the Po River Basin. Next Monday, we don't have lectures. So next Thursday, because it's degree day, I think, next Monday. And next Thursday, we will continue the discussion of this. Do you have any question? Okay, thanks also to the students who attended remotely. See you next time.